You might
Hey,
actually
we're
have,
gonna.
sorry, you might actually have more luck contacting Kim. She's, yeah, she's great.
Okay, yeah, that's actually good advice. So I just started the recording. So for those that might wonder where that started in, we're just asking about things about the program, like taking courses to get bachelor degrees, and when the next set of courses classes are going to be released to sign up for. So thank you for that. Yeah, either Shane or Kim would be good people to contact on that. So thank you. I'm going to get started. I'm going to keep the our kind of business at the beginning here to a minimum because this is a longer lecture that we're going to do today. A couple of things I did want to cover. Number one, it looks like everybody got through the test, so thank you for that. I wanted to remind everybody that in terms of this is our last lecture. The class is slated to be done on December 13th. I actually just went in and adjusted that today. I was given the date of December 13th, but I went in and just tried because I know you guys are uh, busy during this time of year with Christmas coming up and the holidays and all that. So it let me adjust it out to be able to have you guys go through the weekend. So I moved it to basically I'll be closing out the class on the 15th of December. So in terms of like your test corrections, taking the test, all of that stuff, if you could just try to get that done through the weekend so that on Monday, I'll try it probably sometime Monday afternoon or Monday evening is when I'll close out the class. So if you could try to have everything in that you're going to get done by then, that would be super helpful. Um, Other than that, I'm gonna say this particular lecture because we're gonna be heavy on PET. Try to be lighter on CT because PET's the more important component, but we'll still talk about CT today. I can guarantee this lecture is going to go over the hour and a half slot we have. So again, I don't want you to miss out on anybody else's class. So when the time comes, please just log out and I will finish up the lecture and you can follow up with it later. It's just a long lecture trying to cover PET and CT and do it in a way that I think is sufficient enough, but also tries to get in within an hour and a half to 2 hour time range. So we'll try to do that. But again, like I've done before, just log off if you need to, and I'll just move forward. So let me get some slides up and we're just going to kind of dive into it. And then the other thing I would invite is if you have any other extra questions, if any of you are here at the end, I'm certainly happy to ask those. Also, maybe just contact me on your own. And again, I know that's quick, but the only reason I'm doing it is because there's quite a long lecture to cover tonight. So hopefully that doesn't ruffle anybody's feathers too badly. So let me get my slides up and we'll get moving here. Let's see. All right, can you guys see the slides there?
Yes.
Okay. Yeah. All right, perfect. Let me, for some reason my Zoom panel is frozen on the screen and I can't get it out of my own way. Hang tight, I'm gonna stop that share and redo it for a minute here. I don't know why it did that. Okay, let me try that again. There it is. Okay, see my slides again, right?
Yes.
Okay, awesome. Thank you so much. And let me put you guys in a good spot. I can still see you. Okay. All right. So in the Waterstrom book, what we're basically covering today, in one way or another, is chapter 13 and chapter 12. So chapter 13 is PET. We're going to start out with that, and I'm going to spend most of my time on that. At a point in the middle, we'll kind of break into CT and then kind of bring them together at the very end. So that's kind of the plan here. When I get to the CT section, I try to go through pretty briefly. Again, this course isn't meant to get you ready for any kind of CT boards or really teach you the in-depths of CT. We're going to cover some of the basics and how they relate then back to PET and to SPECT and to nuclear medicine in general. Okay. So to start off, PET means positron emission tomography. And I really like this quote. Really, this quote applies to PET, but you could apply it to nuclear medicine in general. But it says the metabolic and biological activities of disease always precede any anatomic evidence of illness. PET as a biological imaging technique adds characterization of simple molecular processes. And I love that because it's really what separates PET to a really specific degree, but also nuclear medicine in general, is that we really look at the metabolic and biological activities, right? We're about the physiology of what's happening, where a lot of other modalities are looking at anatomy and trying to make, a diagnosis based off that, where we get into the really to the biological part of things. And so I really love that quote. It's really what makes NucleMed cool and PET cool, and why we're the best. Don't tell anybody else that, but we are. So anyway, I just really like that quote to kind of start out our PET discussion. So let's talk about the physics of PET. If you remember, we talk about beta plus in one of our lectures that we've already done. Does anybody remember what beta plus is? Anyone want to take a shot at that?
Just a positively charged electron decay, right?
Yeah. So what you have you're not wrong. What you have is you essentially have a nuclide that is rich in protons, right? Super rich in protons. And so because of that imbalance that we talked about, it wants to decay, it wants to get back to a balance. So if you're proton heavy, there's a few things that can happen. One of them is positron emission. And so essentially what happens, if you remember, we talked about this before, that a proton will actually give off a positive charge in the form of a positron. It will kick that off and become a neutron. It will retain its negative and give off its positive. What happens is when it gives that positive off, that positive electron, which we call a positron, it will travel a short distance. It will find a free electron. And for a brief moment, they actually form what's called a positron. It's so brief a moment that you hardly hear it named, but they'll come together, and they come together with such attraction and such force that what happens is as soon as they hit rest mass and they stop their action, they actually have what's called an annihilation reaction. And so their mass is actually converted into energy. And that energy comes out in the form of two 511 keV photons traveling in exact opposite directions, 180 degrees. Now, when I say they travel 180 degrees apart, it's a slight, there can be tiny variance, like 0.03 variance, but they travel apart in opposite directions. Now in PET, we call it positron emission tomography, but we don't actually image positrons in PET, right? What we're actually imaging is that annihilation reaction that gives off two 511 keV photons traveling in the opposite direction. So positron emission tomography is a little bit of a misnomer because we're not actually imaging positrons, right? That's that positive electron, we don't image that. And so that's kind of the basics of what we're imaging and what we're doing. Here's a kind of a better look at that. Now, one thing I want to point out here that's going to be important as we start to talk about nuclides that we use for PET is that remember that this distance traveled, right? I mentioned there's a distance that it travels. When it kicks out, it travels a little bit until it finds that free electron. That distance varies depending upon the nuclide that you're using. So different nuclides will kick that positive electron or that positron off with a little more energy. And when I say energy, I don't want you to think of the energy of like the gamma photons and things like that, but it's an energetic little positron, okay? And depending on which nuclide we're using, that pops off at longer or shorter distances, okay? So what I want to talk about next is I want to talk about some of the nuclides that we use in PET, what makes them different and why that's important or why does it matter, okay? So the ones I've got listed here, we've got carbon-11, we have nitrogen-13, oxygen-15, fluorine-18, and rubidium-82. And in this chart, this is a good chart. If you look at them, you'll notice that these are all kind of like shorter half-lives, right? You got 20 minutes, 9 minutes, 2 minutes. Rubidium is 75 seconds. Fluorine is kind of the longer one, 109 minutes, but they're all pretty quick. And then if you come over here, you have this maximum range and mean range in millimeters, okay? So this is what's describing the travel of that positron when it leaves the nucleus and travels before it has its annihilation. And so what you'll notice is that they all have a different range. So they have kind of a max range. What we're going to talk about mostly today is the mean range. And so you'll notice like the carbon-11, is 0.3, oxygen is 1.5, rubidium is 2.6. So this is the kind of their average or their mean of the range that they travel. Now, why that's important in nuclear medicine, we'll get into in more detail. But what I want you to know right now is that PET nuclides have their own resolution. Now, when I say that, that's a bit confusing because I'm not talking about the resolution of a camera. We'll talk about that today, how much resolution PET can have. But they say that nuclides have a resolution themselves. And what I mean by that is the distance that this travels. Let's go back to our picture and I'll explain a little more. So right here in the nucleus of this atom, right? That's where the actual reaction is happening, right? That's where the anatomy is located, right? So because we're making something radioactive and it's giving off those positrons, right? So that's where the anatomy is happening. However, it travels a distance, again, back to our other screen, in small millimeter distances before that annihilation reaction happens. What we image is the annihilation reaction, which means that the annihilation reaction doesn't happen, or what we image doesn't happen exactly over the anatomy, okay? It happens a slight distance away from the anatomy. And so that's why the nuclide itself has a bit of resolution. And what I want you to notice then is that when you have a lower mean range, that means the resolution of that PET nuclide is better, or it has a better resolution. You're going to get better images from it. So if we look at it that way, we look at something like F18, which you use for your FDG and like your oncology PETs, it's pretty good, right? It's got a 0.2 millimeter, so it doesn't go very far. So it's representing where that annihilation reaction that we image is represented really well in the tissue right where it happened. Whereas rubidium isn't so good, right? Rubidium is 2.6 millimeter range, so it has a little bit more travel. So the resolution of that nuclide itself isn't quite as good as in some of these other ones, okay? So that's the first thing to kind of start thinking about with PET, is that they actually have, and that affects resolution in general, but they have a resolution of their own and they travel, again, before they do. So if you ever get a question about PET, we don't image positrons. We're not imaging positron emission. We're imaging 511 keV. This listed as 0.511, but if we change milli or mega to kilo, then it would be 511. So again, we're measuring, that's what we're seeing. And we're going to talk more about how that works, but that's kind of the basic understanding you need to have. And then understand that there's a range of travel that's different and it affects the resolution of that nuclide. So in terms of production, production of PET, a lot of what you're used to with like your tech is you've probably talked in your pharmacy class about a generator and you wash the column and you get your technetium. So in this, what we need, because we have PET nuclides are created from something that's very proton rich, is we need a way to make nuclides that are very, very proton rich. So the way that we do that is with a small linear accelerators, or you've probably heard them more often called cyclotrons. So that's basically what cyclotrons can do, is they can take protons and accelerate them at such a great speed and then bombard nuclides with those protons and create and have them basically become part of the nuclide. And so it becomes proton rich, and when it does, then it has to start doing things to get rid of it. And of course, in the case of PET, we're talking about it does that by, again, positron emission and then annihilation reaction. You're more than likely have to get, you don't have a cyclotron on site. Some places do, and some of the places you work may have a cyclotron on site. Oftentimes places don't have cyclotrons on site. And so that creates a little problem with what kind of PET nuclides you can use with what you're doing. I'll go back a couple of slides to our half-life. So remember, like a lot of these half-lives are pretty short, so it can make it hard to be able to use a PET nuclide and have it made off site and then delivered to you. About the ones that you guys are probably familiar with that you use in oncology is F18. And again, thank goodness for that 109-minute half-life, right? Because that makes it possible so that it can be made off site and delivered to you. Whereas if you think about rubidium, which we use in cardiology, we can't do that. It's a 75-second half-life, which means, and this is why, but at the back of the PET scanner, we have a generator that sits there, and we basically produce it on site. Now, I'm a little bit mischievous here because rubidium is the one of these. All of these are cyclotron produced except for rubidium. Rubidium actually comes from a generator. It comes from a strontium generator. So it's very similar to your tech, but it still has such a fast half-life that that generator is basically hooked to the back of the camera. We take a line and we hook that line to our patient when we get him in the camera, and we basically have an injector on the actual generator cart itself that gives them the dose. But it's very quick. So it really, a lot of these, you have to have some way of giving it quickly. There's some cardiology is starting to play with using the nitrogen, sorry, long day, with using nitrogen. And so they're actually creating small cyclotrons that you can put on the back of the camera, just like rubidium generators are doing right now, and use nitrogen for stress tests for heart. And so there's things that are happening, but again, that's our limitation with PET is short half-lives, and how can we use those? So let's start talking about how everything is produced with PET. So there's a ring of detectors, as you can see right here, that's in kind of a 360-degree pattern. These ring of detectors are all the way around. So we're used to, with our gamma cameras, and we do SPECT, we're used to having a camera head, and we move that camera head around the patient to be able to get a SPECT scan and produce 3D images that we can slice. In this case, we've got detectors all the way around the ring, okay? We image everything in the axial position, just like in like a CT scanner or an MRI. You're always gonna have a gantry that the patient goes in the axial view. So this is also different than SPECT, because with SPECT, you can move things, you can do some different stuff with the gamma camera, especially when we're doing planar imaging. There's positions that you do, so none of that's gonna be applicable here. It's all gonna be done in the axial position. The other thing to think about is that PET is acquiring in 360 degrees simultaneously, whereas SPECT, again, we're doing it one step at a time. And the reason I bring that up, it would seem really inherent, but as we start to talk about how our images are produced, and how reconstructions are made, it's going to kind of be a little more important to think in that mindset of getting our image all at once, 360 degrees. So PET works by use of scintillation crystals. So it's very similar to what you have in a gamma camera. It is different, and we're going to go over those differences. But the ideal PET materials, or the ideal crystals used in PET, are going to have to be high density. Again, we need high density because remember in one of our first lectures we talked about that we need the photoelectric effect, right? Our crystal has to be able to stop the photons so that it can absorb and measure it, right? So you have to have crystals that are dense enough to stop a 511 keV. In your gamma camera, you're having things maybe from like 140 with your tech to in the 300 range with like your iodine. And so the crystal on this has to be more dense because it has to stop that 511 keV. Has to be really efficient at conversion of photon to light energy. And then it has to be able to produce large amounts of light quickly and then go away quickly so that it can accept more input. So we call that the decay time. It needs a fast decay time. Most crystals don't have all of these things. So we're going to talk about some crystals and kind of some of the first ones they used and kind of what we use now and why they matter. But most of them kind of lack that. So in this next slide, we'll kind of talk about kind of how that all works and what we see there. So what I want you to notice on this chart is we're going to look at the density, right? And then the atomic number. And then we're going to look at light intensity or light emission that comes from each of these crystals, the decay time. And then on this chart, it has that whether they're hygroscopic or not. If you remember from when we talked about our gamma cameras, the crystals on those are sodium iodide and they are hygroscopic. They take water on. That's what that hygroscopic means, is they'll absorb water. Okay, so that's our first one is our thallium doped sodium iodide crystal. And so what I want you to notice here is you've got a density of about 3.7, atomic number 51. This light emission, what they did is it's a relative scale on this chart. So they just said, we're going to compare everything to sodium iodide. So we'll make sodium iodide 100, and then you can kind of see where things go compared to sodium iodide. So the decay time is 230 nanoseconds. What that means is when a photon strikes and that crystal lights up and then is able to go dark again, that happens in 230 nanoseconds. Now, I want to wrap your mind around this because we're going to talk a lot about nanoseconds in this lecture. Remember from our very, very first lecture, we talked about nano and milli and all these different things. Nano means billion. So what I want you to do is take 1 second and I want you to divide it up into a billion parts. Okay, and that's a nanosecond. So that's almost incomprehensible. So when we talk about how fast these things are happening, it's almost an incomprehensible fast, but we'll need to understand it as we start talking about how the camera works and how it's able to gather its data. But just notice that that's 230 nanoseconds. And then, of course, like we said, it's hygroscopic. So in the first cameras that came out, most of your cameras probably don't have BGO anymore, but some of the first ones did. And oh, and by the way, this is bismuth germanate. I'm not going to say all these names because I'll just slaughter it and sound stupid. But there's all the names if you want to know them. In a pet scenarios, talking to other techs, talking to doctors, I've never heard anyone refer to them as their long names. It's BGO, GSO, LSO, LYSO. So that's what I'm going to use. But BGO, you'll notice the density right off, right? So we've gone and we're getting close to like a doubling of the density, which is great, right? Because we're going from using something that's in the 140 to 300 range in our KeV to, again, we need that 511 keV. So we've got more dense, and you'll notice our atomic number, again, more dense on our atomic number. Now, our light emission compared to sodium iodide is only about 15, so not great. Like, that's not great light emission. Decay time is even worse. It's 300 nanoseconds, so not great. However, it is not hygroscopic, so it doesn't absorb water. So this was kind of their first attempt at getting a good crystal that would work with PET. And really the only advantage that they went to this crystal over the sodium iodide is that it was dense enough that it would stop the 511. So when they moved on from that, you get into the GSO, LSO, and LYSO. And so we'll just kind of quickly go through these. But you'll notice, again, pretty good density, not quite as much, but enough to stop a 511. So there's our density. We started to get more light emission. And the real big improvement here is we started to get really a lot faster in its ability to light up and decay. So get a pulse, right? LYSO or LSO and LYSO are probably what are in most PET scanners today. You'll notice the density is really good. You see that atomic number there that reflects that density. And then a light emission started to get even better and better, right? So it's still not quite up to the light of sodium iodide. We're pretty good here with 75 and with 80. You'll also note that the nanoseconds were pretty good. And then again, the same on the hygroscopic. So we have 2 cameras in our PETS department. We got a new one this year. So our old camera had LSO. We had 2 cameras, so one with LYSO and one with LSO. And then now we just replaced the LSO and they're both LYSO. And so, again, kind of understanding what kind of crystal you need and why. And again, as we go on in this lecture, you'll see why it gets more and more important, all of these things, especially this decay time. We'll talk about that. Okay. So here's a page. There's a bunch of information on here. I'm going to actually skip this slide and go to the picture, but I'm going to be saying all the stuff that you see here. So that's just for your benefit. You'll have it. But I want to look at the picture because it's easier to describe. So we're going to look at the actual build of these crystals because they're different than what you have on your gamma camera. So on your gamma camera, remember I mentioned that you had a crystal that covered the entire face of your camera with all the photomultiplier tubes underneath. So what they've done here is the detectors, the crystals, are configured as rectangular cubes. Each of these little portions is about 3 to 4 millimeters wide, right? So that's what you're getting there. And they're about 10 to 30 millimeters long, okay? So scanners have anywhere from like 10,000 to 28, 30,000 of these small little detector configurations of crystals, all the way around the gantry. What they do is they form what's called blocks. So you'll see that this would represent a block that has multiple of these small, 2-3 millimeter crystals in. And what they've done is they put photomultiplier tubes on the back of them. So they'll call this a block. Okay, so you'll have the crystal on top and then the photomultiplier, four multiplier tubes on the back. Sometimes they call it a bucket or a block. And they had two designs. The original design that they had was they cut a crystal with these lines down the middle. And the idea is that they're trying to further locate where the event took place by going into these small 3-4 millimeter little areas. Okay. What they did later to kind of improve upon that design is they actually cut the crystal and separated it out, and then put material on it that is light increasing, or I don't want to say reflective because I don't want to make it sound like it doesn't kind of travel around in the crystal, but it's light enhancing, almost like a reflective type material. And so what that does is it means that these four multiplier tubes are responsible for seeing what happens on all of these little portions of the crystal. But again, because they're kind of narrowing down, it helps the location of where each event took place. It does not work exactly the same as you do with a SPECT scanner, where we kind of see one spot and then we kind of try to calculate based on that spot. And you'll see when we talk about how the camera is seeing the radioactivity and how it's seeing those two 511 events, you'll see how that makes a little more sense. But for now, just understand that they're cut into all these tiny little millimeter crystals on the back of photomultiplier tubes. This is a picture of actual crystals, right? So this is what they look like. So these are 3 millimeter crystals. So those little crystals are each 3 millimeter square, and then blocked together. And then again, you'd have like 4 photomultiplier tubes on the back of that. Okay. All of those are strung together into a ring. And this is what it forms several rings around the camera. So when you look at this graphic, each one of these represents the crystal block, and then they didn't separate it out here, but this would be 4 PMTs, 4 PMTs, 4 PMTs, right? So they're all those blocks, and each block as it goes around forms a ring around the gantry, and you have several of those blocks. The book is going to list 15 to 20 centimeters, creating a field of view in the camera. Our cameras have like 30, I think 30 or 32 centimeters. So again, the book has a little bit of the older data, but somewhere between around 15 to 20, modern like 30 millimeters of view with all those rings. Okay. So again, I'm going to leave this slide right here for you guys to look at, but I'm going to go to the picture as I kind of describe what's going on here, because it's kind of easier to talk about. But this is where we're going to talk about how the camera sees our 511 KEVs and how it works and how it puts an image together. Okay. So what happens is PET imaging is done with a ring of detectors around the board of the gantry, like I've already mentioned. PET uses what's called coincidence detection. Okay. So let's just say this is your gantry, and let's say you have a patient in here, right? And let's say this little dot right here represents where that annihilation reaction took place. And of course, then you had a 511 KEV travel to the right, and you had another one travel to the left. Okay, so these two are going to strike detectors on opposite sides of the ring. Okay, now what's going to happen is the camera is going to see those two events happen, and it creates what's called a coincidence detection by use of what we call a timing window. Okay, remember I talked about the nanoseconds becoming important. This is where they do. So there is a window that is open, and it's between 4 and 12 nanoseconds. Remember, billion, right? So really, really small amount of time. So when the camera sees these two events happen, the first question it asks is, did that happen within a 4 to 12 nanosecond window? If it did, then it will accept those two events as events that it sees and that occurred. And then it creates what's called a line of response. That's what this line here represents. It represents a line of response. So at this point, all the camera is saying is that, hey, I saw an event over here and you saw one at exactly the same time. And when I say exactly, I mean within 4 to 12 nanoseconds. And so we're going to say that an event happened somewhere in between us. Now, at this point, camera doesn't know where the event happened. It just knows there's an event that happened It knows the intensity of that event, and it records and says, we're going to create this line of response. We're going to record that as an event that happened. It's a line of response across the camera. Now, I'm going to skip this part right now because we'll talk about, it's called time of flight, and we'll talk about that later. But first, I just want you to understand that line of response happens, okay? Now, we call this, some people call this electronic collimation, okay? Now, I want you to think for a second, when we talked about our gamma camera, what does our collimators do? Who can tell me, like, what is the purpose of our collimators in a gamma camera?
They're kind of like a grid for X-ray to like knock out non-accurate incoming photons, I guess you'd say.
That's great. Yeah, you're exactly right. I like to use the word knockout. Yeah, we're essentially anything that we knock out, you would say like rejected, right? You're only wanting those parallel events on a gamma camera, and so you're rejecting the other ones that are in at any other weird angle, right? So that's if you think of the word collimator, that's what it does. It rejects unwanted photons, right? Now, even for you guys that have been through X-ray, like even your collimators on your X-ray tube, what do? They collimate the beam, right? So that beam X-rays that you don't want used all on your patient are coned down to a little portion, right? So same thing, a collimator it rejects unwanted photons. So the reason we call this electronic collimation is that what's happening here is that if the camera sees an event and it's past 12 nanoseconds, it rejects that event, okay? And the reason that's the case is because from one end of the camera or one end of the gantry to the other, from one side to the other, is a fixed, maybe it's 80 centimeters or whatever, right? Whatever your camera is. And remember, we're talking about gamma rays. Now, gamma rays are energy, right? Remember in our first lecture, we talked about how gamma rays are energy, radio waves are energy, light that we can see is energy, and really all of that you could describe as light, right? And so a gamma photon, or these 511 photons, if I asked you how fast do they travel, the answer would be they travel at the speed of light, right? All energy travels at the speed of light. And so because we know that, that's why we know that we can say, okay, based on the size of our gantry, we should see two events that happen somewhere in that gantry, we should see within 4 to 12 nanoseconds. If we see something, we see events that we think they happened at the opposite side of the gantry, and they could be from the same event somewhere in here, but it's past 12 nanoseconds, no go. Why? Because the math says that light travels, that gamma rays travel at the speed of light. And we know the size of our gantry for each camera, right? So you might have different size gantries, but part of your camera software is going to know that, right? And so they're going to just form this line of response. Again, it's only going to record something that's within that 4 to 12 nanosecond window, okay? So that's what they call electronic collimation, because we're electronically saying if anything's past that time, we cut it off. Just like in our gamma camera, we're saying anything that's not almost 90 degrees or parallel with the bores, it's out. Just like in your X-ray, hey, if we're going to cone it in, anything that's not out of the cone, you won't see. It won't get to your patient, right? So it's the same idea, but it's an electronic version of that same principle based on those timing windows. And again, that's why there's the need for a crystal that can be very fast, because we have to be able to detect those timing windows to form a line of response, okay?
Is that, sorry,
Yeah, go ahead. Thank you for interrupting me. I like it.
is that 4 to 12 nanosecond? Is that like important time measurement that we should remember, or is that what do you think?
I don't I would know that. Yeah. I will probably test you on that. Like that's a good thing to know for my test. Whether or not you see it on the boards, it's hard for me to say on that. I don't know how much PET they put on the boards and how much they kind of skip around. But I would know that at least the principle of the fact that they're using a coincidence window, understand what a timing window is, what coincidence detection is, and why it works would probably be the most important thing, if that makes sense.
Thanks.
Yeah, thanks for interrupting me. Okay, so let's talk now about, again, I'm going to leave this slide for you guys to look back on. I'm going to cover in the next, but I want to look at the picture again because it's just so much easier to describe things with picture on PET. So there's that slide for you, but it's going to correlate with this picture. So what we need to talk about is a couple of different things that kind of happen when we talk about these timing windows, and you know, nothing in nuclear medicine is perfect. And so we're going to talk about some of that inherent imperfection and then how we deal with it. So this graphic number A represents if we had what we just described, right? So we have this event that happens, it travels 180 degrees apart, 2 detectors on opposite sides detected, it's within the timing window, all is happy in the world, right? So that's what you see there. And that's what we call a true count. And I've listed that over here. It's a true count. We're going to talk about true counts, random counts, and a form of scatter. Okay, so that would be deemed a true count, meaning it looked at it, it happened, it was a real deal. Let's go to graphic C. Graphic C is what we call these random counts. Okay, so what can happen is that, let's say you have an event happening over here on the right side of the body and an event over here on the left side of the body. Okay. So what can happen is if those events happen at almost the same time, which you can imagine, there's radiation in the body, it's happening all the time, right? So those two events happen at the same time. This 511 keV travels and it hits here, and this separate event has one that comes and hits here. It looks like they are the same, right? It looks like they're the same. And I'm going to say in this scenario that those two things hit within the 4 to 12 second timing window. Okay, so that's what we would call a random count. So the computer's going to think, the camera's going to think that that's a true event, but it's actually not. So that's one of the inherent things that can happen. And in a minute, I'll kind of describe the main way that they deal with that. But so that's called a random count. So there's true counts and random counts. And when you're doing a PET scan, and some techs will have this up all the time at different facilities and some won't, but most PET scanners have a curve that you can look at. So you can look at what it's detecting, and it will show you true counts versus random counts, or true events versus random events. And you can kind of see on a curve how much it's detecting of each one as your image is forming. So if you have access to PET, go and check that out, or ask one of your techs if they have anything like that, and you kind of see in real time what that looks like. So that's kind of your two main things that happen. Something else that can happen, it's not a lot, but it does happen. And this graphic is very exaggerated. But it's what we call scatter, and it's not exactly like scatter in X-ray, but also is similar in a lot of ways. But essentially, what you have is you have an event that happens. You have one of those 511 keV photons that cruises off in a straight line. This one starts to, but then there's something that pulls it off that trajectory just slightly. I don't want you to think things like Bremsstrahlung, where you have like it really changes direction. This is super exaggerated. What it would be is the camera's looking for 180. So this is like within 0.5 off or something. Usually it detects within about 0.3. And so this is like 0.5 or 0.6. So it's something has curved it just enough that it's off in its count. And so again, this is exaggerated to look at, but it's going to make it look like this event actually happened along this line of response somewhere. Okay. And so we term that a type of scatter. It's scattering the photons a little bit and creating, again, it essentially creates more random events, right? But we call that a scatter type event. And that's what's represented. If you took the gantry here and then we turn it sideways and we cut it in half, like you're cutting a donut in half and looking down, that's what these represent down here. Now you're going to hate me because, and I don't love this graphic, I need to find a different one, but you're going to notice this graphic has septa on it. I want you to ignore that for a minute. In the original 2D scanners, they did have septa, and we're going to reference that when we talk about it. So don't worry about it right now. But it's just, this is another way of showing kind of what's happening in those events up there. But we will talk about that a little bit more when we talk about 2D versus 3D scanner and what those septa are. But for now, I just want you to understand there's true counts, random counts, and a little bit of that scatter reaction. Okay, so now we're going to start to talk about image formation, and I'm bringing this video up that you've seen already because I need your minds to go back to the principles that we taught you in SPECT, because these principles are going to connect the same way. They're a little bit different in their acquisition, but they're going to be the same in how we're able to put our images together. So I'm going to play this again. Remember, we talked about filtered back projection. So filtered back projection is used in PET, and iterative reconstruction is also used in PET. Okay, so I'm going to play this video again. Just to remind you, this is going to show the acquisition of a SPECT scan, and then it's going to show the reconstruction of the SPECT image. And so we'll click on that here, and I'll pause here in just a minute when it's kind of pulls up to kind of remind you. And I know you've seen this. If you've watched it a bunch of times, I apologize, but it's helpful for what we're about to discuss to kind of get your mind back to this spot. And hopefully you understood this, at least to some degree. So what we have here then is we're going to see the SPECT camera go around at different angles and get projection data and gather it in a sinogram. Okay, so I'll push play on this. Remember, as that travels around, we start forming a sinogram, and each sinogram is one slice, so one of these little areas. So there's many slices happening, but this represents one slice each sinogram, okay? So that was the acquisition. Now this is the reconstruction part. This is where we talked about we throw a projection across the matrix. And I'm going to pause again because I want you to remember this picture, okay? All this picture represents is that one slice of that anatomy saw all these different intensities and it threw it across the matrix, okay? It just threw it once across the matrix. And what happens again when we do filter back projection is we keep throwing those as the camera goes around the body. We throw those over, and areas of activity that overlap become brighter, and areas where there's not activity fade away, and then at the end we filter it, right? So here's let's just let the animation go. We came up at the end, by the time it did all the projections from the SPECT camera with the same thing. Okay, so keep that in mind. I mean, let's go to our next slide here. Okay, so let's bring you back to this idea of lines of response, okay? So we mentioned that this event happens. We have our annihilation or our coincidence detection that happens on both sides. It's within the timing window. And so the camera says, I'm going to form this line of response. Now, as you can imagine, from this event right here, you don't just have that one response, because remember, how does radiation travel? It travels 360. So from that one response, there's stuff going everywhere, right? And then there's multiple events happening within the body part you're imaging. And so, I mean, you've got lines of response going all which ways, like 360 all over the place, okay? So it formed this line of response, but the other thing it did is it would have formed another one there within the anatomy, and another one there, and there, and there. And what I want you to notice here is that these particular lines are all parallel to one another. So even though there's stuff going everywhere, what the camera will do is it looks at these lines of response, it looks for lines of response that are parallel to one another. And then what it does is it takes those parallel lines, and remember, they hold the intensity, and they know it happened along that path. They don't know where. And so what they do is it performs a filtered back projection, just like SPECT. It puts it across the matrix. And again, the camera doesn't have to move to then put the next one across the matrix, because it's all happening all at once, all the time. So the computer just looks for those parallel lines, and then it starts to form images based on that. That's what I tried to represent down here. If you had a SPECT camera, the SPECT camera would take a picture here, and then it would move here, and then it would cross all of those on the matrix, right, and form our image. Well, PET's just doing that, but it's just gathering that data all at once, all together, okay? You can start to see again why those nanosecond times really matter, because it's doing all of this at one time and then recognizing which lines are parallel and forming sinograms out of that data. That's what here's another way to represent it right here. So this is the SPECT comparison. Again, your camera takes a picture here, records the data, here records the data, and then this is the idea of that data is thrown across the matrix. This data is thrown across the matrix. Again, same thing happening with PET. These parallel lines are thrown all together. These parallel lines are thrown together, and that's forming a sinogram, just like you would see for SPECT, right? So in SPECT, we had the image here went on top, the next one went down below, the next one went here, and the next one went here. So same thing, this is a SPECT image you're seeing right here, but same thing happens with PET. It's just gathering all that data at one time during the acquisition, right? But it does it exactly exactly the same. And I wrote that here. So the PET data acquisition stores in sinograms. Each horizontal row represents the count or the profile or projection across the gantry. And then that projection is taken over 180 degrees. So it's really the same principle. We just have to think a little different in terms of how the data is gathered. So again, lines of response thrown across the matrix. Now, the reconstruction is filtered back projection is used. Also, iterative reconstruction is used. If you remember, just to kind of remind your minds, iterative, what it did is it looked at the projection and then it made a mathematical guess as what the next projection should look like. And it kept doing that until it got it right. Again, the reason it did that is because then you don't have to use as much filtering and it's very precise on what it puts on the matrix. Whereas filtered back projection, again, has to be filtered at the end so that we can get rid of all the extra stuff around the edges, right? And so your book mentions by name a few of the iterative reconstruction algorithms that are involved in PET. And so you have the maximum likelihood maximization, which is MLEM, the ordered subset, expectation maximization, which is OSEM, and then the row action maximum likelihood algorithm, RAMLA. And so I've heard these mostly referred to as the acronym name and not that full long name. I think there are possibly some, I will not test you on these specifically to know what's different about these. I do believe in some of the practice tests that you'll do at the end of the, in a practice book that we'll give you to go through to kind of prepare for boards. I do remember there being some questions on this. So it's something you'll kind of want to sort of understand in the back of your head. Whether it's on a board or not, I'm not sure. That's pretty detailed into PET, I would think. But just to kind of give you a brief, short explanation on those, essentially what happens is the MLEM, you basically have, it takes 20 or 30 iterations and it uses all the data required, but it just grabs a small like subset of the data and uses it to reconstruct. It's supposed to be a faster way of doing it. It's maximum likelihood. Somehow it cuts out some of the math by kind of mixing between filtered back projection and iterative reconstruction. The OSEM is also very, very similar. It uses like a smaller subset of the data. I think that the ordered subset is more math heavy and the maximum likelihood is more filtered back projection heavy. And then that RAMLA one, it's more of a vendor specific one. I can't even remember. I think the book mentions it, but I don't know that it explains it. I think they're similar to the other ones where they use kind of a mix. And essentially what they're trying to do when they use a mix of the two is try to cut down the time that it takes and the computer power that it needs. Because again, these are reconstructed. We run some reconstructions in cardiology that sometimes you have to wait like several minutes for these reconstructions to happen. So then you can pull up your data and start to process it and get it ready for the cardiologist to read. So they can just take time because again, tons of math data happening here and tons of computer power needed. So again, I don't think you need to specifically know these, but kind of know that there's different algorithms out there. And there's even more than these. There's some that are vendor specific that are neither of these or none of these. But again, I only put these in here because your book does mention them. So you can take that for what it's worth. But I would just know that, again, filter back projection and iterative reconstruction, same as what I've taught you, but just thinking about lines of response. Okay, we need to talk about time of flight. Okay, so, and I'm gonna do the same thing. I'm gonna leave this data here for you to look at, and we're gonna look at the picture again. A picture had time of flight earlier, and I told you we'd come back, so now we're coming back to it now. So this is kind of a further advancement that has happened in PET when we talk about the lines of response, okay? Now, remember earlier, I talked about the camera knowing how big your gantry is and then also knowing the speed of light. So as crystals have gotten better, again, when we start getting into the early cameras weren't able to do this. The newer cameras can. So this is probably like your LSO and your LYSO crystals can do time of flight. In fact, our first camera that we had in cardiology, in our nuclear cardiology, was an LSO, and it did not have time of flight just our LYSO ones. So maybe it's just LYSO crystals. I should look into that. Anyways, what we need here is crystals that are really quick on their timing, right? Their timing windows can be small because they're really small in their nanoseconds. And so what they've done is you still have a line of response here, but the camera software is going to take into consideration the length of the bore and that speed of light, and it knows from the center, if you were to have an event happen right in the center of the gantry, the camera knows how much time that should take to get to each side of the gantry. And so it pre-calculates and it knows exactly how long it takes for that time of flight to happen, right? So then what happens is if you have an event that's, in this case, it's slightly to the left side on the patient. So you have an event that's over here. And what the camera knows is it's going to see within the coincidence window, the 4 to 12 seconds, it's going to see this event, it's going to see this event. But it's also going to know exactly how long it should take in this camera from the center. And so it calculates, it says, well, I saw this a little faster than I expected to from center. And this side of the camera says, I saw this a little later than I expected to from center. Again, still all within the timing window of the 4 to 12 seconds, right? And so because it knows that, it can then say, all right, based on us comparing our times, we can guesstimate or estimate, and time of flight can work within about 9 centimeters. We can guesstimate where that event occurred within about 9 centimeters. So that's what you're seeing represented here is a 9 centimeter line of response. Over here, they represented it as kind of like almost like a bell curve, right? So the highest probability, it's like a probability curve. It's the most probable that the event happened here, but there's some probability based on those times that we compared that it could have been within this 9 centimeters. So the computer can be good enough with those timing windows that it can see it within 9 centimeters. And that's what time of flight does. Now, how does this cause any advantage? The reason it's a really big advantage is that now our line of response is still there, but when we're forming our lines of response for our projection data, it's only going to do that within a 9 centimeter area of where it sees it, right? So it's still going to perform back projection or iterative reconstruction, but you're going to not worry about all this other data out here. You're not going to worry about anything on the line of response going this way or going this way when you reconstruct. So you're going to be reconstructing with a much smaller area, which means if, for example, you are just running straight filter back projection, you're going to have way less to filter out because no data would have been seen out in the rest of the gantry anyways, only what will be in that 9 centimeters. If you're using the math, again, it doesn't have to calculate based on everything it sees, but only on that 9 centimeter section. So it really improves the resolution and the ability of the camera. It also can improve the speed of the camera and how quickly you can get do an acquisition as well as especially the reconstructions. Okay, so that's time of flight. Most of your newer cameras within, I would say, probably the last 5 years or so probably have time of flight. It could be a little longer than 5 years. But anything you get new, like if your facility picks up a PET scanner, I can almost guarantee that it's going to have time of flight, and that's what that is. And it's a big advancement for that reason. All right, so we're going to talk about the difference between the 2D and the 3D scanner, and this is where we go back to talking about those SEPTA and the differences. And I've got kind of got the data and then a picture, much easier with the picture, so you can reference this data. But if you look at these pictures, what you're seeing here is this would be like the Z-axis. This is how the patient travels through the scanner. So again, we've taken the donut, sliced it in half, and turned it so we're looking kind of sideways through. The original scanners, what they did is they actually put SEPTA, lead SEPTA in here, very similar to what our collimators in a gamma camera does, right? And what they were trying to essentially do is just limit any kind of like scatter and random events down to one small area for the crystal itself. So these were like the blocks, right? So each of these was a block. So, that square block of the multiple 3 millimeter crystals. And it was just trying to limit data to one small area. One reason they needed to try to do this is that the computers weren't quick enough. And so you had to try to get everything, each photomultiplier tube to kind of have its own little area to look at. What they did in later versions and what the difference is with a 3D scanner is they removed the septa altogether. And this is where really understanding PET and how amazing it is in terms of sensitivity starts to really play in these 3D scanners. Because what happens when we were viewing like lines of response back here, we were viewing them kind of going this way through the camera, and you just kind of assumed, at least I did when I was first learning this, that this was just kind of traveling straight across this way. What the cameras can do now is it can see lines of response throughout the entire field of view. So in other words, if an event is happening here, and again, X-rays or gamma rays going 360, right? Those 511s are traveling every which way. That means that this crystal over here, if it has an event and it came from this center over to here and the other one went over here, it can use those events from crystals that aren't even in the same ring. Okay, so it can use events from anywhere that it sees them as long as it's within the coincidence timing window. This ups the sensitivity by like a factor of like 10 from just what the 2D scanner was. The other thing that to think about is when you go from a SPECT scan, this is one of the reasons why PET is so sensitive and so much better. When you go from a SPECT scan, the resolution on a SPECT scan is somewhere in the neighborhood of about 12 millimeters. Whereas a PET, you're getting down to like 3 and 4 millimeters, okay? So the resolution is much, much better. And then this speaks to the sensitivity because remember, when we talked about the principle of sensitivity, what I said is sensitivity is measured by how much available radiation do I have coming off, and out of that, how much do I actually gather, right? We talked about how, a well counter is awesome because it's almost surrounding, and so it's super sensitive, right? You gather a lot of the data. That's what you did here is you increased sensitivity. So again, this is going to increase the sensitivity. It's going to increase the ability of to gather all of the data happening. It's going to up your scan times, like that you can gather data so quickly because it's all of these lines of response are being gathered rather than just a few that are straight across from each other. Okay, so that's the difference of a 3D scanner. Now your scanners today, they're going to be all 3D scanners. I would be surprised if you had a 2D PET scanners. They're pretty much old and gone. Again, it's probably possible. I don't know all the facilities, so it's possible that you have a 2D scanner, but it's not likely. And any scanner you get today is going to be 3D, which is why I didn't highly focus on these SEPTA when I was teaching you, because everything nowadays is the 3D and the 3D principle. Okay, so awesome for reconstructing data, awesome for speed, and for sensitivity. Sensitivity goes way up. And here's that kind of now comparing that PET to SPECT and some of that I just mentioned. Again, significantly higher in sensitivity, in resolution. This is why PET is so much better in SPECT. Here I list, I don't know if you guys remember when we were doing, I actually listed it here, count rate on a gamma camera, and I said the efficiency was like 1% because of all the stuff we have to cut out with our collimation. We're only gathering like 1% of data. The PET count rate, and I looked this up, this is actually what's listed in your book, but I think the book is listing a 2D scanner. They say it goes up to like 2%. It's much, much more than that. But they say it's about 50 to 100 times more sensitive going to PET versus SPECT. So this is kind of where you get so much better images and why PET is in a lot of ways taking over a lot of what SPECT does, and I'm sure we'll continue to do that in the future. All right, so we're going to take, I've gone for an hour. Let's take a 5-minute break. We'll come back at 5:05, and then we're going to try to do a brief CT area and then connect back to PET after that. So I will see you, let's just say 5:05, okay?
Thanks.
Yep. All right, we're gonna go ahead and get started again. I am unmuted, right? You guys can hear me?
Yeah, I can
Okay.
hear you.
Okay, thank you. All right, so like I said, we're gonna get into CT. I want to re-emphasize here. There's one aspect where I don't think you're going to be highly tested on anything CT when it comes to your boards. I think to know some basics and how they interact with Nuke Med is the most important part, and we'll cover that. However, you're not going to be able to avoid CT as a nuclear medicine tech. Most cameras have a CT attached to them now. And if you get new ones, they'll almost certainly have CT attached. So understanding some of the basics, I'm not going to get deep again, like this isn't meant to be a CT course and get you prepared for CT boards. So I'm going to cover things relatively briefly. There's quite a few slides, and so I've given you a lot of information, but I'm not going to cover it as in detail as I would when I'm going through our PET slides and the other slides I've been through. I'm going to try to be quick because I don't want to keep you guys forever. Like I said before, we've got about another 25 minutes till you're done. So when you need to cut out, cut out. I'll go until I'm finished, but we'll try to get through it quick and then get back to how it relates to PET. Okay, so for most PET CT scanners, this is kind of a classic PET CT looking or scanner and how they're built. Usually you have your CT gantry on the front end, and then your PET is on the back end, and they're just connected into one unit. So this will be covering chapter 12 for CT physics and instrumentation. So I want you to think of SPECT and PET are emission data. What I mean by that is you're making the body radioactive, and you're emitting, and then we're gathering that data with a camera, whether it be a PET, SPET, or oh my gosh, I can't talk, gamma camera or PET camera. And then CT is transmission data. And what that means is that with CT, we're shooting X-rays through the body part. The body attenuates some of that, and then we have a detector on the other side that gathers that data based on the attenuation that happened within the patient, and that's how we form our image. Same with X-ray, right? That's a transmission data. And so we might kind of reference those two terms as emission or transmission, and just to understand how they're different there. So a CT scanner, just kind of quick design. You've got your computer, you've got processing computers, you've got electronic cabinets. The main thing we're going to talk about is the gantry, which houses the key components, which are your X-ray beam, your X-ray tube, anything that's done with detection. And then, of course, you have an imaging table that goes through, right? So here's a picture of the inside of a CT. You'll notice you've got your X-ray tube up here. You have collimators. We'll talk a little bit about, there's a couple of different types of collimators that can be in a CT scanner. And then you've got detector, what they call a detector array. So this is the detector that gathers the transmission data coming through. Okay. When CT scanners first came out, they were what's called a pencil beam. So it was just a simple one beam with one little detector. Basically, it would start at one end of the patient. It would do a scan, move, do a scan, move, do a scan, and then that would rotate, and it would do the whole thing over and over again, and they took forever. And so from that first generation, they've come with a second generation where they added a fan beam and more detectors. And basically, they've continued that process until you came to what are considered third generation, which is what most CT scanners are today. They have a fan beam or a cone beam on the X-ray. You've got what's called a detector array, and it's a range of detectors, of multiple detectors. And basically with this system, you have the continuous movement. So you'll have your X-ray and your detectors move around the gantry at the same time, right? So images are really quick on a CT scanner. Couple of different types that are important to know, and the book does not do a good job at deciphering these when it's describing the principles. So I'm trying to kind of help clear a little bit of the mud. And I'll do that on a couple of different things here, but there's conventional, or what's sometimes called axial, or sometimes you'll hear it called step and shoot. And that's where the CT tube will go around, it will take an image of the patient all the way around, and then the table will move, and then it will image and move and image and move, and it's stepping and shooting as it goes along. Again, this is along the Z-axis, so the patient travel through the tube. And then you have the helical, or sometimes called spiral, sometimes called, yeah, those are two main ones, probably helical and spiral. But this is where essentially the table moves continuously through as the gantry continuously X-rays that goes around. So it's more like a ring rather than a step and shoot. There's kind of key components that made helical and made it so that you could have multi-slices, and so that that continuous motion of the gantry and the ring can happen. One of them is that you have X-ray tubes that are built different than kind of the X-ray tubes you guys use in X-rays. They're much bigger and heftier, so they can handle being on over long periods of time. The other one is what we call a slip ring technology, and I'll go to a picture to describe what that is. That's a pretty cool thing. And then of course, continuous motion of the imaging table, continuous data transfer also happens with a CT scanner. So it's transferring the data as it's imaging. Again, that wasn't possible until computers got quick enough, but it speeds up that whole entire process. This next picture is of a slip ring. And the way I would describe this is here in Salt Lake, they have a light rail tracks, right? And so you've got off the cart, it has a little kind of antenna that goes up and rubs along the wires, and that's how the cart gets its power. So this works very similar. You have a ring inside the gantry, and then you have a brush block. So you can't see underneath this, but there's a bunch of brushes that are contacting the ring. And this allows the ring to continuously turn while those brushes give it power. And then there's also electronics down here that have brushes that are receiving and transmitting data, right? So it's transmitting the data all the while that CT scanner can just sit there and turn and turn and turn. And that's because of this slip ring technology. Another thing to define between the kind of types of CT scanner. So I mentioned you've got the step and shoot, you've got the helical. So within both of those, either one of those can be what we call a single detector CT, which is where you have one row of detector arrays, or you can have a multi-slice or multi-detector CT. Now, most of the stuff that you look at today is going to be multi-slice. These are the old scanners that had a single row. However, I will give the caveat of that some of your older gamma cameras that do have a CT on may be only a single slice. And so they take a long time. We use them for attenuation correction, which I'll get into in a minute. But some of those will still have a single row of detectors on them. The reason I make the separation is because when we talk about some of the other things with CT, it matters if it's a single detector or if it's a multi-detector. They function a little bit different. Not a lot, but a little bit. And these two can be the conventional step and shoot, or they can be the axial helical, right? Either one of these can do either of those, but you can have that multi-detector or the single detector. So this X-ray tube, the vast majority are probably very familiar with this. I'm sure that I could pick on one of you and you could give the lecture on this, so I won't cover this in depth. But essentially, you have a cathode and an anode on the sides of an X-ray tube. Then the cathode, there's a filament that creates what's called thermionic emission, which is where a bunch of electrons gather up. When there's a voltage applied across the tube, it pulls over to the anode side. You've got a rotating anode that's usually made of tungsten. When those electrons strike that tungsten, we create a couple of different types of radiation, which we'll talk about here in a minute. That's where we get X-rays. So very similar to what you have in your X-ray tubes that you're all familiar with. That you probably will use. So those two types are the two types of radiation that we need to think about in production are Bremsstrahlung and some characteristics. So Bremsstrahlung comes from a German word meaning breaking, and what that means is that an electron, again from that thermionic emission and getting pulled across the voltage from the cathode to the anode, it comes in close to the nucleus. The pull of that nucleus pulls on it. It doesn't do anything, it doesn't interact, but it turns and it breaks, or it breaks and changes direction, okay? And when that direction happens and that slowing down because it gets close to the nucleus, that's when it gives off X-ray photons in the form of what we call Bremsstrahlung, again, breaking radiation, okay? The other thing that can happen in an X-ray tube is characteristic X-rays. And again, that's where a K-shell electron is hit. And when that happens, then shells above it fall into place and you get characteristic X-rays that come off. Okay, sure, most of you are familiar with those as well. We need to talk about KVP, and then we're going to talk about MA. And with KVP, this is your voltage, this is your push, right? Higher energies of KV are going to help us penetrate tissues more deeply. You know that. In PET CT, we use KV ranges anywhere from 80 to about 140. Advantages of the KVP are ones you're probably familiar with. Again, greater penetration through the body. We decrease quantum noise because we get more photons through when we have appropriate KV. The book is going to say higher dose to patient, and I know you guys are used to thinking that if you have good KVP, you're not leaving photons in the body, and that's true. I think the book is just saying all other factors remaining, that when we increase the KV, we kick off more radiation from the tube. So I don't know why the book says that, but just know that that's why I put higher dose to patient, because there's more that can come out with higher KVs. That's actually what these represent. The other thing I want you to understand that at least I didn't understand when I went through X-ray until later as I was studying, is that we call it kilovoltage peak, meaning that the highest energy, when you set it to 140, the highest energy that it's going to kick out is 140. But it's going to give a big average of energies that come out of there, right? It's not like everything that comes off there is exactly 140 kVp. So that's something to look at. And so, you know, when you do like a 60 kVp, you're getting a range that's peaking at 60. 100 is peaking at 100 and 140. And then just as a GWIS fact, this is the spectrography of kVps and of photons coming off. This right here, you might be like, what the heck is that little spike? What that is that's the characteristic X-rays right there that are popping off. So the K shell of tungsten has about a 69 keV energy. And so that's why you see this kind of somewhere in around 69, 70. That's that characteristic X-rays there. The other one is MA. Now, for you X-ray brains, notice I didn't say MAS, right? Because MAS stands for milliamperage seconds. That's true on X-ray. CT is different depending on how you're imaging, right? Because we're talking about how the table's going through. We're going to talk about how the gantry spins. The time is determined by what you're doing with the gantry, not necessarily just by seconds. So when we talk in CT, we just talk about MA, milliamperage. And because of that, you're going to notice when you do MAS, you times the milliamperage times seconds to get what you actually read is like, well, I'm going to do, you know, 30 or 40 or whatever. Whereas when we're talking about CT, we set the MA, not the MAS. So you're going to have bigger numbers. So CT ranges anywhere from 550 to 400 MA. Again, that the seconds are going to be smaller. So it's a little different. We're going to talk about low dose. We do a low dose on our MA to save patients, and it works for attenuation correction in low dose. We'll talk about why that is here in a minute. But higher MAs increase patient dose, right? And if we lower it, it decreases. However, when we get enough photons coming through, MA raises up the amount of photons. So we're going to get better images when we get the right amount of MA. And again, I know you guys all kind of know that difference between KV and MA. And I'm not going to test you on that. And I would doubt that you were tested on that as well. But just understanding when you go to use a gamma camera that has a CT attached onto it, you need to understand what you're looking at and why. Okay, so that's KVP and MA. I want to show you some of the effects here on CTs that we can get. So notice my I have kind of on A here. There's 80 kV and there's 200 MA, and you'll notice that we get a little bit of what we call quantum noise, and it's kind of that modelly look. And the reason here is we have enough electrons coming through, but our KV is so low that they're not getting through the body. So we're probably giving our patient a really good dose right here, but not getting great images. A better would be to get really good contrast resolution to be, here's a CT at 140 kV with 200 MA. Now you've got nice, pretty pictures, and you've probably given less of a dose to that patient. Down here, you have what's called a ring artifact. What's happening here is you notice that I've got my KV low and my MA low. What you actually are, what's causing this ring is that one of the detectors in there, or it looks like actually multiple, they're actually not even firing off because we're not getting enough photons through the patient that some of the rings aren't getting sensitive and firing. And so you're getting rings that are firing and rings that aren't firing, or detectors that are firing and detectors that aren't. And as that travels around the patient and makes its image, it forms those ring artifacts that you see. This last one, it's kind of the opposite of the first one. We've got 140 kV, so we've got a good KV, but again, we're not giving a whole lot of MA, so there's not a lot of photons, but they are penetrating and getting through the patient what limited supply is there. Now, in a CT scan, if you were going for a diagnostic CT, you'd be like, this doesn't look good. We got quantum noise. We want it to look more like this. However, we're going to talk about in nuclear medicine and SPECT scans and in PET scans, the use of what we call a low dose CT and why it works. And so we'll get to that, but we actually are going to use KV and MA settings that are very much like this, and we'll kind of connect why we can do that later. Okay. All right, so the X-rays also have a filter. You're probably familiar with this on your X-ray machines as well. These filters are a little different than X-ray filters, but essentially what a filter does is, remember I mentioned back here that you have a spectrum of energy coming out. So some of it is energy that's not very penetrative, down on the low end, and some of it's energy that's very penetrative. What we want to do with a filter is a filter blocks some of the weaker X-rays from getting to the patient. We call that beam hardening, meaning that we're making the overall average that's coming out of the beam more towards that higher powerful end. And that's good because we want it to be able to penetrate through the patient, right? So that's what we call beam hardening. So a filter can reduce exposure to a patient by as much as 50%. Now, in a CT scanner, they have what's called a bow tie filter. And what the bow tie filter is it's a certain type of filter that's in a shape. Now, remember, in X-ray, you measure the body in all kinds of positions, and you move your tube, and you move the person, right? But remember, in CT, just like in PET, we're always imaging in the axial position, which means our patient is going to be in the exact same position all of the time. So what we do is we have this filter right here that's kind of in the shape of a bow tie. And essentially what that's trying to do is match the patient body habitus. Every patient, and I know this is, patient body habitus are different, but overall, when you put a body through, you're going to have the thicker portion of the body in the middle and thinner portion of the body towards the edges. If you let the X-rays come out and penetrate the body, what you're going to see is that towards the edges, you're going to get more X-rays coming through, and towards the middle, less. And so you'll get images that don't look evened out. What the bow tie filter is doing is it's not only cutting out all the low end stuff, but it's also cutting a little bit more out on the edges and letting a little bit more through on the middle so that it can even out those images that are always going to be in the axial position. So again, that's a bow tie filter, a little different than what you're used to in X-ray, and that's why it's there. Filter location is similar to X-ray. It's going to be kind of just right outside the tube. This is just an energy spectrum to show again that what happens when you filter the low out. What you'll notice here is overall we've reduced X-rays coming out of the tube. But what I want you to notice most is that we've eliminated them on the lower end greater than what it eliminates them on the higher end. And that's what we want. Because all this stuff on the low end, all it does is increase patient dose. It doesn't help us form an image because it doesn't even get through the patient. It just exposes them to radiation, right? So that filter helps kind of shift everything up towards the higher energy range. Our detectors for CT are essentially what they do is they create an electronic signal in response to X-ray. They're solid state detectors, so they're not working off like a gas filled or a crystal based, but they're solid based detectors. And I'm not going to get into the physics of exactly how those work. But they don't use either of those two technologies that we talk about, but they are sensitive to radiation exposure. And so again, I've got a single slice detector array here, and then this is like your multi-slice. So this Z-axis is how the patient travels through. So you'll have this kind of detector array of multiple detectors and multiple rows. Now you might hear people say like, how many slices does your CT scanner do, right? And oftentimes before I kind of studied it out, what I thought that meant is that I thought it meant how many of these rows I had was how many slices. And that's sort of true, but it's actually not. What defines the number of slices that your scanner can do is actually the number of data channels that you have. So in a 16 slice CT scan, you have 16 data channels that can simultaneously take the data and send it to the computer as the imaging is happening. You might have more than 16 rows on your detector. You'll notice on this one, you have like 4 bigger rows on each outside edge. And then in the middle, it's basically like they've taken 4 more. Actually, there's, how many is there? 1, 2, there's 6 of them in there, and divided them in half to now there's 12 smaller ones. So in this case, you can select which of these you want for each of your channels. You can combine ones and say we want that on this slice channel. You could only use these center ones and make it into kind of if this had enough 16 channels in the middle. And it depends on what you're imaging. So for a lot of the detector arrays that have something like this, where they have some bigger ones and some smaller ones in the middle, those smaller detector elements allow you to get finer objects, right? They allow you to take finer images and smaller images. And the ones on the edge, again, not as much. So you have a bunch of variation that you can do, but when you hear someone say they have a 16 slice, it means they can produce those 16 slices at a time, but it doesn't necessarily mean that's how many detector rows you have, okay? So collimation we need to mention really quick, and there's kind of 3 types, and these are a little different based on whether you were running a single slice or a multiple slice. And again, you're going to do multiple slice detectors is what you're going to use nowadays. I'm including this because your book doesn't make the distinction, and it's super confusing when you're reading it. So the first one for the pre-patient collimation, this is collimation very similar to your X-ray tube, that it collimates the X-rays coming out of the machine, and it collimates it to whatever you've set your detectors at, right? So that's pre-patient collimation. And it just kind of aligns the tube with the detector. Then there's post-patient collimation. And what that means is that in your single slice, it actually has these little collimators that are right before the detector that kind of open and close. And on a single slice CT, that's what determines your slice thickness, is the opening or closing of that, because it'll get less of your detector exposed or more, right? So on a single slice, that's the only way slice thickness is determined. On a multi-slice, the purpose of a collimator is actually really similar to our collimators on our gamma camera. It's there to cut out scatter. So it's just before the detectors, and it just makes it so that any scatter radiation from the patient is kind of being cut out by this post collimator there, okay? So it doesn't have anything to do with how slice thickness or anything else. It's just getting rid of unwanted photons from scatter. And then the last type is detector collimation, or some people call this the kind of electronic collimation, not quite like PET, so I don't want to confuse you there, but detector collimation, which is essentially where it's controlled by either the electronic combination or separation of individual detector rows. So this is what I was talking to you about earlier, where you've got all of these options you can do. Like here it shows that it's got, let's see how many is on here. 1, 2, 3, 4, 5, 6, 7, 8. So this represents 8 channels, right, that you can send data on. And in this case, whoever's doing this scan, what they've done is they combine these two detectors into one channel. So that's going to be a slice. These 2 detectors as a slice, and then they've combined 4, 4, 4, and 4, and 4, and then 2 and 2 again to get those slices. And then they've taken the same detectors down here, but they've cut off those outside edge ones and just put all 8 of their channels on the smaller detector configuration, right? So this is collimation based on what you're turning on and off, and what you're detecting, and what you're choosing to allow to be on and open on your detector. And that's detector collimation. The other thing we need to talk about is rotation speed. So rotation speed is just how fast the gantry rotates around or how fast the X-ray tube and the detectors rotate around. If all other factors remain the same, then the faster your X-ray is on, that would reduce patient exposure. Now, we put out a certain amount of kV and MA, and so again, the book's going to talk about it that way. But all other factors being the same, rotation speed, making it quicker, would reduce the dose, right? This is when you're used to X-ray, used to MAS. This is your S portion, right? It stands for speed and not your time, but it's kind of the same idea. So reduces patient exposure. The other thing is if we have fast rotation speeds, we can reduce patient motion artifacts, right? If we can do it really quick, it's less likely that your patient moves in between rotations and slices as the camera is going along. It improves throughput and very good for cardiac procedures. As you can imagine, when you're imaging the heart, you really can't stop it from beating, right? So you're going to have some inherent motion. So the quicker you can make your rotation speed, the better images you're going to get in cardiac. The other thing we want to talk about is pitch. And pitch is basically a ratio of how fast the table is moving and how fast your rotation speed is around the camera, okay? So to give you kind of an idea of this, if we had a pitch of 1, so if the thickness represented, let's say this is not the right numbers, let's say it represented 1 millimeter, or let's say it represented 5 millimeters, you could really do anything you want to say it was 10. And if this represents 10 millimeters thickness, then each time it slices around, the table is going to move 10 millimeters so that it never overlaps and it never misses any data, right? So that would be a pitch of 1. If we went to a pitch of 2, you would say, okay, I've got 10 millimeters slice thickness, and I'm going to move the camera 20 millimeters, and so now that would give you a pitch of 2, right? If you had a pitch that was less than 1, that means you're now overlapping body parts. And so kind of the disadvantages and advantages here is that when we have a pitch that is smaller, we are gathering, because of the overlap of data, we're getting much more data of our scan, so we can produce a really pretty image. However, your dose is high here on the patient, whereas when we go to a higher pitch, like a pitch of 2, we're reducing dose to the patient, but we're gathering less data, right? You're still gathering it all the way around the patient, but you're gathering less angles, less projections across the same data, so you can't form as good of an image. Okay, so that's pitch. So when you're using your PET scanner, you're going to have pitch on there, and it's going to determine what's happening depending on what type of scan you're doing. Okay. And I put a picture in here. This would represent like a single slice, and this would represent like a multi-slice where there's multiple going around, at the same time, but the principle is still the same. Okay, the other thing we need to talk about is the Hounsfield unit. Okay, I mentioned that CT is transmission data, right? Transmission data works because we're sending an X-ray through body parts that have different densities, and so they attenuate more or less of the X-rays. And where there's denser object, X-rays don't get through as well, and where there's less dense objects, they do, right? So you have what's called a linear attenuation coefficient, and that's just a representation of X-rays coming through, how much attenuation did the body have happen, right? So it's attenuation. It's a number that represents attenuation. So in a CT scanner, attenuation coefficient values end up being very small numbers because there's a massive difference in tissues and parts to attenuate, right? So I'm talking things like it's like 0.003, right? So we're way out to like the thousandth place. Attenuation coefficients also aren't the same from camera to camera because your camera is a little different. Maybe it gives slightly, one camera might have a little bit different energy level than the other, even though they're similar. You might give out a little bit type of a different X-ray beam. Maybe your X-ray beam is a little harder, and the next camera over here, CT scanner, their beam is not so hard. And so you're going to have differences across equipment as well. And so this can cause problems and differences in looking at anatomy and looking at processes of depending on what you're trying to diagnose on a patient or whatever. So what CT has to do is it has to find a way to be able to represent attenuation values so that it can reconstruct an image, while also at the same time finding a way to make it so that you get a CT scan over here, you're not going to have something completely different show up if you go to a CT scanner over here. So what they do is they're going to create what's called Hounsfield units. What a Hounsfield unit is it's a CT number that is calculated for every machine relative to water. Okay, so in the morning when you guys do you warm up your CT scanner, you set a phantom on there, and in that phantom is water. And what you're doing is your machine is scanning water, and then what it's going to do is it's going to represent water as 0 Hounsfield units. Whatever that attenuation value is for your machine, it's going to say, I'm calling that 0. And the machine across the next building over, they did the same thing. They're going to measure water, and whatever their number is, they're just going to call it 0. What this does is it makes it so that machines are going to see the same thing depending, no matter which CT you are on, because they've measured water and then made water their starting point. Okay, so anything that is more dense than water is going to go to the positive Hounsfield units. So things like, here's the heart, somewhere around 10 to 60 Hounsfield unit, all the way up to bone. Bone can be, depending on the type of bone, anywhere from 1,000 to 3,000 Hounsfield units. Anything lower in density than water is going to get a negative Hounsfield unit reading. So you've got like lung is like 850 to 200, errors all the way down to 1,000, right? So your Hounsfield unit range goes from about negative 1,000 to about positive 3,000. And again, it's all based on a comparison of water, and that's how it can calculate its attenuation value and be the same for machine to machine. Image acquisition is very, very similar. I won't really go into it a whole lot, but essentially you're gathering transmission data and you end up with projections just like you do in with your gamma camera and your PET scanner. You end up with projection data that you then create sinograms on, that you can use those sinograms to then reconstruct images that you want to see using, again, iterative or filtered back projection, or there's a lot of, with CT, there's tons of proprietary manufacturer base, they call them kernels. Often you'll hear that word in CT, they call them kernels. And so again, but it works in a similar way. Reconstruction works the same across all three, with the variation differences of how it gets its projection data. Now, kind of one of the last things we need to talk about is CT display. Remember, I mentioned there's a wide variation in Hounsfield numbers from like negative 1,000 to positive 3,000. So you have this huge amount of attenuation values that you have to try to find a way to represent on an image and display that. Now, the human eye, it only can discern between somewhere where they say between 30 and 100 different shades of gray, from white to black, right? That's all of our eyes have the ability to do. So that number, that 70 different shades, is a whole lot less than what these actual attenuation values, these Hounsfield units are, right? So how do we display that? What do we do? Now, one other thing that causes a problem is that you've probably heard in other, studies in your X-ray and things that you are often limited to 8 bits of data, which equals out to be about 256 different intensity values on a computer screen, okay? So we've got this big discrepancy between Hounsfield units and what the camera can display in different densities as it shows disease processes, bone, lung, whatever, what we can actually see, and then what our computer can produce, right? So to make up for that, that's where we get what we call our grayscale window. And you're probably familiar with window and leveling. You've probably done that with your X-ray. What's happening in a CT scanner is it's taking the Hounsfield units, and if you represented the Hounsfield units on this scale here, from again, negative 1,000 to positive 3,000, it allows you to have a window, and you can move it on the Hounsfield scale to which part of the Hounsfield scale you're wanting to view, okay? And what that does is whatever your window, wherever you've placed your window, it then takes those Hounsfield units and puts them into the 256 shades of gray, okay, for you to view. That's what a window is doing. Now you can also have window width, which just means that you can make this window really narrow and be representing just a small amount of those Hounsfield units with the 256, or you can widen that window and represent a lot more of those Hounsfield units with the 256 gray shades, okay? But that's what you're doing when you're window and leveling. So to give you just kind of a quick couple of examples, this is the same scan. This is not a different scan, different patient, different anything. It's all the same exact scan, but what we've done is we've moved it into different windows. So you'll often see on a CT scanner, they'll say like, I put this in a bone window, or I put this in a lung window or an abdomen window, and that's what you're seeing here. So for the bone window, you'll notice that our bone, you can really, really see well, like it's really defined. You can see the spine, you can see cortical area of the bone. Everything's really well done, and that's because it's in a bone window, which is down around 1,000. But you'll notice here that like you don't really see the lung very well at all. Like the lung, it just looks like dark. It's kind of just nothing there. If you go over to a lung window, which is getting closer to like a negative side of the Hounsfield unit, like 0 to 1,200 negative, you'll notice now that our bone doesn't look good. It's terrible. We can't see anything, but look at how well you can see all the bronchioles and everything that's going on in the lung, right? And that's because we just changed our window. Again, the data is present on the CT because we have all those bazillion Hounsfield units and attenuation values, but we're just telling the computer, hey, I only want to focus on these ones because I don't have the ability to do that with my eye, right? And so here's an abdomen window too, and you can see down here, if you go down to the abdomen section, like the liver over here in the bone window doesn't look good. It's kind of too muddled out. The liver over here in the In the lung window, it's just, you can't see it at all. It's just whitened out. And then here in the abdomen window, again, you can see different densities and variations. You would be able to see, if there was disease process in here, things like that. So that's how the CT display works in our different windows. Okay. Last thing, real quick, just CT artifacts. Artifacts can happen. 3 primary sources that they say are operator, do something wrong with your scanner. The scanner itself is having an issue, or patient, for things like patient motion and things patients are wearing and all that kind of stuff. So that's where you can get artifacts in CT. And then the last thing I'll say with CT, I keep saying the last slide, but this really is, I think, the last one. Quality control, of course, is required on a CT machine. It's required by the Joint Commission as well as the ACR. And there's some specific vendor stuff as well. But the ones I want you to kind of know that you probably do on your CT scanners that you do or don't, may or may not have on your gamma cameras, is you do a daily X-ray warm up, right? And that's to make it so that our tube doesn't crack. We need to warm it up before we use it on a patient. You'll also have the phantom acquisition that has water in it. Again, that's you measuring to get your accurate Hounsfield units for the day. And then the last one is that will be done daily is system calibration. And the system calibration actually just measured X-ray from the X-ray tube to the detectors just in air. And it calibrates the system to make sure all the detectors are seeing the X-rays in a kind of a uniform way. So that's done daily as well. All right. So we made it through the X-ray portion. Some of you may have gone. It looks like some of you are still here. Now we're going to combine them, and this won't be that long. We're going to kind of connect them and kind of bring them home. I want you to think of this. We just went through a bunch of CT stuff. I think it's good for you to know it for your practice. Don't necessarily need to know it all for your test. What I do want you to know for testing purposes and to think of why CT is important in PET is really there's 2 real purposes, okay? One of them is that we get perfectly aligned images and we can really see anatomy. So here's a PET scan. And what's so cool about this is you've got the CT here, you've got the PET here, and then you've got the 2 combined. This is awesome because for like a whole body PET in oncology, you're looking for cancer, right? You're looking for lesions. And this is beautiful because we can locate, we give our patient FDG, which is a radioactive glucose. That glucose uptakes in those cancer cells because cancer is super active and hungry. And now we can locate it and we can see exactly where it is within the anatomy. And that's just awesome. I don't know about you guys, I'm a total nerd, but if I would have seen this when I was like 8 years old, these kind of pictures, I would have thought that I was in Star Trek or something. Like I thought I would have been like, geeking out about it because it's so cool what we can do when we combine these 2 imaging modalities together and what we can see within the patient. And so PET CT is combined. Now we're going to talk about attenuation correction because so that was the first thing, is we can see anatomy really well. The second thing is attenuation correction, and that's kind of what I want to get into now. So attenuation correction, there's 2 types, and I list them down here. There's 2 kind of things that we use it for, or two types of attenuation correction. One is with use of a CT, and we're going to talk about that first and how it works. And then the other one is a transmission scan using a radioactive source. And we'll kind of mention that too and show you examples of both of those. But as you can imagine, the problem we run into and why we need what we call attenuation correction is that your body, when you put stuff into the body, right? And let's say you're doing a heart. That's just what's on my mind most. You're doing a heart and we've given you rubidium, and that rubidium travels to the heart muscle and attaches in. You have to think of the different body habituses of patients, right? Especially with the heart, what we're trying to find out is that the rubidium travels and it goes anywhere where blood flow goes, right? And the whole thing we're trying to detect is if there's areas of the heart muscle that are missing blood flow, you're at risk of heart attack and things like that, right? So you can imagine, and a good example is female patients. Like a female patient might have like large breast tissue. You can get patients that are just kind of larger in general, so they'll have a lot more adipose tissue. And so as you're trying to image through that, we know that the photons are coming off, and that the whole thing we're trying to do in new med, whether it's with gamma camera or PET, is we're trying to detect those photons accurately and trying to detect their intensity accurately so that it represents the same intensity of however much has gathered in certain areas of the body, right? So if you have a breast tissue, that's going to block some of that radiation more on maybe the anterior of the patient than it would maybe on the lateral side of the patient. So if I've got my PET scanner and I've got lines of response going all different directions, some of those lines of response are going to be attenuated more on the front than they would on the lateral side, right? And then they would on the back. And so you're going to get a representation of intensity of radiation that's inaccurate because it's attenuated by the body. And so what we can do is we can use CT, which is transmission data, and we can use that to our advantage to correct for attenuation. So here's kind of the example. This graphic A would represent the actual, it represents radiation coming off the patient, but it represents the patient habitus. So what I'm going to say is that this dark area in the center would be an area where the patient maybe had some more body fat or more tissue. And we're going to say these light areas are where it's not so much. So when we pulled this up on our PET scanner, it might appear that this area that's being attenuated is kind of darker, and we've got much more like bright activity around the outside edge, okay? However, when we run it, what we do is we take our CT scan, which is represented here in graphic B, and we lay our CT scan over the top of our PET scan. And what we've done with CT, remember CT is transmission data. So how did a CT work? Well, it worked by denser objects stopping some of the X-ray photons from making it to the detector. So what do we have? We have a bunch of attenuation values based on Hounsfield units, right? So what we can do then is the computer can look at the CT data and it can say, I know exactly where there is thicker body parts, and I know exactly where there's thinner body parts. So what I'm going to do is where I see thicker body parts, I'm going to add a little bit of activity to the PET side of the scan or the SPECT side of the scan, right? So that when you combine those two and it makes up for that attenuation, you get an image that looks more like this, where even though there's some sort of thick body part in the middle, it's not blocking out and attenuating any of the PET data. And so this is extremely helpful for us in nuclear medicine, right? Because our whole gig is being able to detect radiation accurately, of what's happening inside the body. And so again, with different body habituses, you've got attenuation that's going to happen naturally, but the CT is going to correct for that. Okay. So we use CT as transmission data. The other thing that we can do is we can use a radioactive source for transmission. And before PET scanners had CT, this is what they would use as this transmission source. So what happens is when your patient is in there, most PET scanners have, and it's usually germanium, they have a germanium source in there. And what would happen is they would put that germanium source out, and they would rotate that germanium source around the patient and detect everything that was happening. And this could be done on SPECT as well. So you're detecting transmission data as that germanium source gives off radiation and it goes through the patient's body. You're getting all those attenuation values. And then it works exactly like CT. It compares the two, and it makes up for where it saw more or less attenuation by giving some back to the PET or back to the SPECT to even out the image. Now, on this picture here, what I want you to notice on this top image, this is a PET scan. There's no CT data here. Remember, we're just looking at PET data. What I want you to notice is it appears in this image, if you look, for example, like these arms, it looks like there's a lot of uptake in the arms. It looks like there's a lot of uptake kind of up in the sternal notch and area, on the top of the shoulders. You can see the lungs are quite dark, right? For some reason, they're kind of darkened out. And there's areas that are kind of brightened and white. And so what's happening here is, remember, with a 511 photon, it's very, very powerful. And one thing I want you to think about when you give, and this is the best example of this is the whole body FDG. When you give FDG, the G part of FDG, the first part is fluorine 18, the G part is glucose, right? It's a sugar. So when I give you the sugar in your body generally distributes that sugar throughout the body, and then it gathers more in areas where you have like cancers or things like that. But it goes throughout the body, which means because your body distributes sugar everywhere, you have 511 photons that are coming out of that arm, and they're so strong that essentially what they're doing is they're just making it look like that arm is just hot, because there's no attenuation in the arm to stop anything from coming out. There's just not enough tissue here. And so it just looks really hot because it's seeing a lot of that data with no attenuation. Whereas by the spine or things like that, it's attenuating a lot more. And so it appears there's less there. There's not less there. It's just attenuating a lot more. But the 511 is really strong on these thin areas that are coming out in the lungs, right? Lungs are like, there's hardly any attenuation in the lungs. So that 511 is just blowing through those lungs, right? And that's why you get this darkness. When you take the picture down here, this is where they've taken that germanium, radioactive germanium source, which was transmission data, just like a CT, and they've applied it attenuation correction. And now you notice, like, look at the difference in the lungs. The lungs are represented here and they're dark. Here they're lighter, like you would expect a lung to look like. Look at our arms. Everything's evened out. There's not this heavy stuff up by the sternal notch or up on the shoulders. But you're still getting activity in these areas where there's actually activity, right? So there's a lesion here, and we're still seeing that lesion, right? We're seeing those things. That's actually bladder right there. That I think is a lesion though. Anyways, but you can see the difference in look how much better the spine looks, the liver looks better, everything looks better because it's evening out that attenuation correction. Okay, so that's with a transmission source. And most of your modern PET scanners still have a transmission source in them. But it's usually used for part of a quality control, and we'll talk about that in just a second here. So that's attenuation correction. I wanted to show you a couple of quick examples. So this is one we have in cardiology where we have our PET data here where the rubidium gathered in the person's heart, and then you have the CT in the background. And depending on how big a screen you're watching, I don't know if you can see this, but you can see like this line right down here. Okay. It's a motion artifact on the CT. The patient probably kind of moved a little bit. And so one of the slices kind of jolted and missed. And so it looks like there's not like the CT super light right through there. We didn't notice that at first. And so we processed our images and got our slices up. And what you're seeing here is you're seeing the heart, and you'll get more familiar with these images next semester when we talk about hearts, but essentially, the left ventricle is displayed up here and sliced up right into what looks like a donut. And so what you can see here is that in the lower this is the inferior wall of the heart, which again is where we're seeing this down in the inferior wall of the heart. It looks a lot lighter in the stress scan than it does in the rest scan. Okay, and this image right here was the stress. So you're seeing this area where it looks like there's less rubidium gathered. And so we're thinking, oh, hey, this patient's got an area where they've got reduced blood flow in the inferior wall of their ventricle here. So this is like looking like it's a little bit more on the positive side. However, as we were looking through all the other data that comes along with PET scan for a cardiac, it wasn't making sense. It looked right, but all of our other ancillary data was like, this doesn't seem like it's a problem for this patient. So we went back and looked at that CT, and that's when we noticed this little jump right here. And we thought, I wonder if that's causing problem. So what we did is when we do our scans, we do when we do a resting blood flow and a stress blood flow. So the resting blood flow has a CT associated with it, and the stress has its own CT, right? So what we did is we went back, and instead of using the stress CT on the stress scan, we grabbed the rest CT and we used it for our attenuation correction. And here's what we got. Let's see. Here we go. Okay, here we go. This is the picture I want to show you. So this first one is the rest again. This is our first time that we produced the stress scan with the stress CT. And then we redid the stress perfusion with the rest CT. And lo and behold, look at that. Look at the difference. It filled right in. Why? Because what was happening is this CT error was causing an error in the attenuation correction values and making it look like the patient didn't have blood flow in their inferior wall when in fact they did. Okay, so this is how CT can be important. This also demonstrates why we need to look for and understand CT artifacts as well. Okay, kind of a marriage of the idea of these two together. Just a few slides left. We're almost done. Again, if you need to go, I more than understand. We need to talk about what's called the partial volume effect that happens in PET. Okay, so what happens is you get a partial volume effect when we get the size of something that we're trying to look at on a PET scanner, like let's say a lesion on an FDG scan, when the size of that lesion starts to get close to the resolution of the PET scanner. So remember I mentioned the pixel, or not the pixel, the crystal sizes were about 3 or 4 millimeters on most. What's represented on this graphic is 5 millimeters. So I want you to think of this as kind of your crystal, the end of your crystal, okay? And so when an object starts to get close to the size of the resolution, it starts to get what's called a partial volume effect. And what we mean by that, if you look at the biggest, like say this is a lesion right here, right? And it's represented over these several 5 millimeter crystals. What's going to happen is that a crystal is either going to see something or not. It can't break apart what one crystal sees. So one crystal is going to represent how much activity it sees, and that's what it's going to portray on your image. And so these crystals in the middle are completely full with this lesion. So right, this is going to represent accurately really well what's happening. But as you start to get out to the outer edge of this lesion, what's going to happen is this particular crystal, it's going to average what it sees. So there's part of the lesion in here, but then there's part that has nothing. So instead of being able to, you can't break that up in one crystal. It just, the crystal has to give the average activity and represent that in brightness on your scanner, right? So as you get to the edges of things, when they're not represented within a crystal, they can get a little bit lighter. That gets more problematic the smaller you go, right? So here, we're going to still see this lesion because it's represented by multiple crystals. We get down to this small one, and what you're seeing here is there's really only 4 crystals that see it. And in a couple of the ones on the right, it's barely represented. And the ones on the left, it's represented, but certainly represented by non-activity is more representative in these crystals. So when these 4 crystals try to represent this, there's 2 things that are going to happen. One, it might kind of totally miss part of this lesion altogether, but it at bare minimum is going to represent it as less bright or less activity than it actually is, because it averages everything across the volume of that crystal. Okay, so that's what the partial volume effect is. Just something we need to be aware of. And kind of the rule to keep in mind that with the partial volume effect is you cannot see a lesion on a PET scanner that is smaller than the resolution of your system, because they're going to get too small to be represented and they're going to get less and less bright. Over here on the right, this is a JSAC Phantom. We talked about that during spec. You can use a JSAC Phantom on a PET as well to test, but it's got these spheres or balls inside a kind of a cylinder shape. And what you notice is that there's the same amount of radioactivity throughout all of the balls. But what you notice is you come from these bigger, brighter ones, you can really see them really well. So the spatial resolution is really well. That represents kind of this bigger one. You can see it nice. As these spheres get smaller and smaller and smaller, 2 things happen. One, you start to not be able to see their distinction in terms of resolution as well, but you notice that they also get less intense in their brightness. And it's not because there's really less radiation there. It's because, again, that partial volume effect, it's going to average things out and it's going to represent it as less. So that's one of the kind of downfalls of PET, especially when we start talking and looking into lesions and things, is there's a certain resolution in the system, and that resolution really is determined by those crystal sizes and then this volume averaging effect. Okay, so remember, that's a good thing to remember, is you can't get a better resolution than what your pixel sizes, or excuse me, what your crystal sizes are on your scanner. The other thing we need to talk about with PET is SUVs, and you may have talked about this if they've gone over PET. Can't remember which scanning class you're on or what's taught first, but if you talked about oncology PET, you've probably talked about SUVs. But this is something that's really cool about PET, is that we can actually quantitatively count or measure how much radiation is in a certain area. And this comes into place really a lot when you do an oncology PET. So I mentioned earlier that you use FDG, you use glucose, that cancer cells are really uptaking that glucose. And so one of the things we want to know is the more active a cancer is, the more sugar it's going to want to consume and take in. And therefore, when we put FDG in a patient, the more FDG that uptakes in a certain area, that means that cancer is either more or less active, right? And if you have a patient, you want to be able to stage that cancer. And when they're going to have a PET scan, we're going to see what their cancer looks like. And then they're going to go through treatment. They're going to come back for a PET scan and they want to know, hey, is this helping? And the problem is if it's just based on viewing something, you might be able to be like, well, I can still see that lesion, but how active is the cancer? That's the question. So that's what quantitative can give us. So an SUV is a way to measure the ratio of concentration of activity in a certain area of the body that we define with a region of interest that we make around, whatever part of the body we're looking at. The way an SUV is calculated is they take that region of activity and it's divided by the dose that you injected over the body weight. Now, I mentioned earlier in the lecture that when you give FDG, a radioactive sugar, it evenly distributes itself across the body generally. And then within that, it's going to collect in those areas of higher activity, right? And so the reason that you divide it here is your ROI is saying, I want you to compare this spot to the dose that I injected, and then I want to consider how much of that's dispersed throughout the body. And that comes up with a number of how much of your original activity is in that specific spot that you've looked at, okay? And we call that an SUV, or a standard uptake value. And so we can measure how much radiation is in one area of the body. And that's why it's important when you're doing PET scans that you're measuring your dose right before the injection, you're measuring your dose right after the injection, you're measuring the time of injection, and you're measuring body weight and height accurately, because SUVs are dependent upon all those factors, right? To get accurate SUVs, you've got to be able to calculate all of those things because you're considering decay and you're considering the habitus and size of the body to get that ratio accurate. I'll skip past some of these. So I didn't have any whole body PETs. You should look at those. If any of you have an oncology department, go visit them. But I can show you one thing we do in cardiology that's kind of cool. So this is a scan that we do where we look for inflammation in the heart muscle. And inflammation in the heart muscle, what happens is if you get part of your heart muscle that's inflamed, that inflammation kind of pushes on the vessels in the heart. And what you'll get is a reduced blood flow to the heart. And that can look like, like you're having an issue with coronary arteries when you're not. It's just inflammation. And so we have to find a way to be able to look between what's coronary artery disease and what is inflammation. So what we do is we actually give the patient FDG, but before we do that, the heart uses fatty acids for its substrate of energy, right? It prefers to use fatty acids, heart muscle does. However, if there's not fatty acids available, it will use glucose. So what happens is we have the patient eat a really high fat, high protein diet and then fast. And essentially what we're doing is we're making it so that the healthy heart tissue that's not inflamed is really happy to take that fatty acids. When you have an area where there's low oxidation, so if you have inflammation and you're not getting very much blood flow there, there's not going to be much oxygen there. You need oxygen for the oxidation process to happen when you break down fatty acids. So what that means is that areas that are inflamed, even though you're giving it a bunch of fatty acid, it can't eat it. And so it's like, man, I'm starving over here. Then when you inject FDG, because it's a glucose, it can use glucose. And so all the healthy tissue is like, hey, man, I'm good. I got all the fatty acid I need. And that inflammation is saying, I am hungry, so give me that glucose. And so that glucose will gather in that inflamed tissue, and then we can measure it and see how much is in. One of the things we do to qualify to be considered inflammation on cardiac tissue is we measure a background SUV value for the dome of the liver, and we compare that to any hot spots we see. And it's supposed to be a 2-to-1 ratio. So in this case, we measured the liver and it's 1.9, and then we measured the hot spot we saw in the heart here, and it's 2.48. So even though we see a hot spot, it doesn't qualify as a 2-to-1 ratio. It's not quite there. Here's another scan that we did. This is a whole body of a patient where we looked at these 2 areas of the heart and said, is this inflammation? When we measured those, we got an SUV value. The dome of the liver is 1.9, we got an SUV value over the cardiac tissue in that hot spot. We can see a 4.6. So this qualifies, and this is likely inflammation. Same thing with here. So there's many ways that you can use the standard uptake value, not just in oncology, but in also cardiology. But again, it gives us quantitative data that we can quantitatively do something with, which is really cool. It's an awesome thing about PET. The last bit, I just wanted to show you kind of some unique things with how they display PET data. This is especially true in oncology where we look at whole body scans, but you can construct a PET and a CT in any of the planes that you need to, whether that's sagittal, axial, coronal. And that's awesome because it gives you an ability to look for lesions, look for problems. Usually a PET scanner, especially on oncology, will display all three of those views at the same time. And we'll give you these crosshairs. So there's this hot part up in the axilla there. If I click on that, it will orient every one of the images to that same spot. So this is awesome for doctors that are looking for lesions and cancer and trying to identify and then getting SUVs. They can really hone into where it is exactly, which is just awesome for PET. I've also listed just the calibrations that you do and when you do them. So that, let's see if I want to. Whoops. So the ones I want you to think about mostly, and you can kind of look at these. I just listed when. I doubt you'll have to know exactly what all of these are, but this energy window just looks for that the camera is set to look for 511. Again, it's the only energy that's going to be looking for in a PET scanner, so that's a calibration that a service engineer does. The gain settings is one that's performed weekly on the PM tubes. What happens is you'll have a radioactive source that will go into the PET scanner, and what it will give off radiation, and then it will look at the gain. It knows how active that source is, and then it will look at the gain on the PM tubes to see if they're reading similar, and it will level them out if they're not. Coincidence timing calibration is done by a service engineer, and he comes in and makes sure your timing windows are accurate and that all the measurements across the gantry are accurate. The other one that you'll do daily along with the gain setting is what's called a blank scan. And the blank scan puts a radioactive source into the middle of the scanner, and then it checks all of the lines of response across the scanner. It's the closest thing I would say to like your daily floods that you do on a gamma camera. It's very similar. It will check to see that all of the detectors and the buckets are all reading in a uniform way. Normalization is very similar, except for it goes longer. It'd be like your 30 million floods, and it will go in and not just check for a daily if there's anything out, but it will also go in and it will normalize and even them out. If it sees any slight differences in the way the crystals are seeing things, it will go in and with that long extended flood, it will even out the camera and how it's working, very similar to normalizations or 30 millions when you do them on gamma camera. And then absolute activity calibration is done quarterly. Sometimes it's called a well counter calibration. And that's one that checks on SUV values. So you have a phantom, and you put that phantom is a certain volume size, and then you put a certain amount of radiation inside of it, and the camera knows the volume of that container and the amount of radiation, and then it calculates SUVs and makes sure that all of the scanner is accurately calculating SUVs across all the crystals. Okay, so generally, again, I highlighted those two that you probably do on a daily basis. This can be done daily, weekly. Our oncology department was doing it, I think, daily. I think we do it, or maybe they were doing it weekly. Anyway, can't remember if it was cardiology was doing one or the other, but they can be daily or weekly. Blank scans are definitely done daily. So just kind of know those generally. And this is what a blank scan looks like. This looks like a single flood image. That's not actually what it is. If you were to pull this up, you can actually, it's really, really long. So I would be scrolling through this image. And what these lines represent is they represent the possible, they represent a line of response from one detector side to the other. And so if you get one that's out, that means something's happening there, that line of response is not being detected. And this is formed in a sinogram. So that's why you see some lines of response going this way and some going this way. It's because it's just taken and put a sinogram. So this thing is really long. If you look at a blank scan, in your department, if you have a PET scanner, just ask your tech. You can kind of scroll through it and it just goes over and over. It's really super long, but that's kind of similar to your floods. Radiation safety in PET, I will say that it's a much higher photon, so I need to be aware of that. The same principles of ALARA apply. The best thing you can do to be safer in PET is increase your distance from patients, right? So if you inject a patient and they've got to circulate for 2 hours, don't sit in there and hang out with them and shoot the breeze, because you're going to get a high radiation dose exposure. So I'll just kind of leave that simple at that. Distance is most effective. I put that here. I mentioned some of the other things that we use. Some of the shields around syringes are tungsten rather than lead because of the 511 keV to block it. And that is it, my friends. That was very long. I see some of you like held through to the end. Way to go. I'm going to stop my share. And then I'll briefly take any questions if anybody has any. If not, get your class done and we'll get grades out. And I'll see you next semester for cardiology.
Awesome. Thank you so very much.
You bet. Have a good one.
Thank you.
Thanks for holding strong.
Thanks. See ya.
Okay, see ya.